This is a features and overview of an AiM MXM Datalogger device. As you can see here, we'll go ahead and power on the unit. So you can see the unit going through its startup sequence here. We do have connected to one of the CAN inputs, an LCU-ONE wideband oxygen sensor. You can see the sensor, the Bosch LSU sensor there. This is the provided user guide that comes with the MXM Datalogger. You can see after it boots up here, the home page that it's displaying will have a bar graph as shown here for your engine RPM. It has 2 dedicated warning lights at the top, as well as 5 programmable shift lights. These are programmable in color and programmable in terms of features or thresholds in which they activate. You can have these as shift lights or as predictive lap time lights. And then a few of the fields here showing the battery voltage for the supplied battery voltage, the RPM, which this isn't connected to an engine currently, and then 2 of the 4 available analog inputs. Currently they just have PT100 water temp sensors plugged in, so this is just showing ambient temperature here. So some of the available connections here on the device, if we flip it around, you'll see the provided 37-pin DTM connector, or the Autosport connector, as well as this particular connector here, which is for the power distribution functions of this device. So there's 2 configurable 15 amp supplies or channels here that you can power 2 devices with, and you can monitor the voltage, the circuit status, as well as the current for each of those channels independently. The harness that's provided has inputs for an array of different ECUs, be it RS-232, CAN connectivity, or as well as K-line, depending on the ECU. There's a dedicated RPM input, and then 2 dedicated pulsed inputs for speed signals that you have as well. And then, as I previously mentioned, there is an expansion port, or a CAN expansion port, for things like an LCU-ONE or the AiM SmartyCam system, any of those devices, as well as another CAN input that you can use for ECU connectivity for non-AiM devices effectively. The screen itself is a 268 by 128 pixel, similar to what's found on the Micron 5 suite of devices. And the 4 fully configurable analog inputs are high-speed inputs that are 1000 hertz each. So those are high-quality analog inputs itself. The GPS sensor is actually built into the device here. That's 10 hertz GPS sensor with a inertial 3-axis 5G accelerometer, 3-axis gyro, and 3-axis magnetometer. There's Wi-Fi connectivity on this device, as well as USB connectivity, similar to legacy devices, and 4 gigabytes of onboard memory. So we'll simulate what will happen. One of the nice things with RayStudio 3 to test things like configurations, as well as alarm thresholds and things like that. You can simulate an RPM input, and because we have an LCU-ONE connected, right now it thinks that the engine is not running, because if we scroll through to the next page here, this is the current air-fuel ratio being read by this Bosch sensor, just because it's in free air, obviously, and this is showing the diagnostic status for the O2 circuit. So because it's in free air, as soon as we simulate an RPM, it's going to think the engine is running, and it's going to warn us that the engine is lean. So what we're going to do is simulate an RPM of 7,500. And you can see that instantly it will warn us that it's lean. The 2 warning lights will start flashing red, and one of the LEDs on the RPM bar graph has been illuminated. So if we scroll back to the home screen here, you can see that this bar graph is showing indications all the way up to 7,500. So we'll simulate now to remove that alarm. We'll simulate stoichiometric operation, so an AFR of 14.7 here. So I'll scroll back to that screen, and now the 2 warning lights here have stopped illuminating. The warning symbol has gone away, and these have changed to green, meaning that its stoichiometric state is what this is measuring. The intention of this is to somewhat simulate a motorsport AFR gauge in terms of the way that you're visualizing AFR. Without actually looking at the number here, you can visualize kind of the state of tune of the engine mixture for their fuel ratio. So we'll continue to step up the RPM. We'll go to 8,000. You can see the second RPM shift light has been illuminated. Go to 8,500, just in a stepwise format here, and you can see the live RPM incrementing here. We'll go 9,000. 9,500. And then we'll exceed the rev limiter, and we'll go to all the way to 11,000 here. So you can see as we've exceeded the rev limiter, we're above the 10,000 threshold. All the warning lights are illuminated currently. The intention of this is just to show later on the device we can scroll through the data log and actually see each of these RPM step inputs. So if we scroll to the next page, we're still sitting at 14.7 AFR. Let's simulate an AFR that's more indicative of what you'd see under wide open throttle. Let's say 12.5. Now the warning lights here have gone to white, indicating that this is kind of the normal state of operation for the device under wide open throttle. Let's say if we go even richer to an AFR of 11, these are gasoline AFR equivalents obviously, and it's going to warn us that something is wrong with the mixture, and the AFR is rich, and both of the warning lights will be changed in color to blue to indicate to the user that issue. So I will stop forcing the channel value here. It's going to show what's the free air equivalent of 1.6 Lambda or 23.3 AFR, and it's going to go back to warn us that it's lean. So I'll also stop forcing the RPM channel input here, and I'll show you. Currently we've had 3 minutes and 4 seconds of simulated RPM input, which have triggered the data log. So I'll stop forcing that, and you'll see there'll be a little bit of overrun here on this particular counter. Then it's going to stop, so it collects a little bit of data after the RPM signal goes away, and it's going to show us that we had 3 minutes and 16.79 seconds of runtime for that particular lap. This is the total session time. This is the current GPS speed. This is the altitude, which is unknown because we have 12 satellites. We're currently indoors. This is a mileage-based odometer. The battery voltage, the RPM, which we're no longer simulating, so it's 0. Both of the temperature analog inputs, you can obviously add all of the 4 analog inputs here. The current lambda, and that same equivalent in AFR, and then the lambda temperature and the diagnostic circuit. So I'll scroll back to the home screen here, and we can go through the data log that we've just collected. So if we click memory, and we click one of the test sessions, so 922 is the most recent test session here. You can see 3 minutes and 16.79 seconds, the maximum and minimum RPM here. If we were to be racing around a track, we'd obviously have a non-zero GPS signal, so we'd have some meaningful data here for max speed and mile per hour. But we'll click page, and then we can see that initially we started, this is showing a bar or just a chart or graph here of the RPM versus time. So we started at 7,500 RPM at 0 speed. So we'll just step through the data here. You can see in terms of seconds, we're going to keep jumping forward until we started stepping up the RPM there in increments. Probably around 1 minute here. So you can see we're at 7,500 RPM. And we can keep scrolling through the data. Now we went to 8,000, and we can keep stepping through the data. 8,500 at 1 minute and 20 seconds, 1 minute 30 seconds, 9,000, 9,500, and then finally 11,000 at 1 minute and approximately 50 seconds, let's say. Obviously, you'll be able to see the mile an hour as well if we were actually using this outdoors and racing around a track. So that shows you effectively 1 lap of data there, and you can post-process it directly on the device without actually connecting it to a computer at all. So that's quite convenient, and it stores all of the sessions here in different files, obviously, as well as different days. So that's convenient. I'll go through some of the quick configuration options that you can see on the device here. You can change the backlight color, and I'll show that quickly by forcing the device to blink through all its available colors there. It does have Wi-Fi connectivity that you can configure on the device as well. You can do track management on the device. Specific counters for different engines on the vehicle, or different drivers or different weekends, different tracks. Currently this device is brand new, so none of this has any populated data. Date and time, language, and then you can visualize the serial number and the firmware info in the system info tab here. So that was a brief features and overview of an AiM MXM device here with an LCU-ONE connected. Once again, the available CAN expansions for this device are an LCU-ONE Lambda controller, as well as any of the Smart Cam suite of devices that AiM offers.